in most cases, one does not know the angle of arrival of the electromagnetic wave, and then you cannot use the trick we used last time to create a reflectionless end of a coaxial line. So if the conditions are general, so that you do not know the angle of incidence, nor you know the velocity of the wave that propagates, then we should use other ways. One of those is something which is called a matched layer. Now this is an important concept that we should...
Pardon, jenom
Yes?
jestli můžu vyrušit, já u sebe nic nevidím, nevím, jestli něco promítáte nebo tak, ale
Aha,
já nic nevidím.
děkuji. Já si myslím, že promítám, tak já to ještě jednou zkusím. Can you see me now?
Ano, teď už vidím.
Thank you, okay, sorry. So the first important point is the reflection. Let us describe the reflection in the case of a perpendicular incident wave. So we have a boundary between the air, for example, with characteristic impedance or wave impedance 102.20 pi ohms, and some material which is now designed to not reflect the wave. But how to do that? So we have there another material with some impedance. I will put, say, ZA, like is impedance of the absorbing material. And we have to have a finite grid. So for example, if you describe an antenna, you create something like a big grid. There is the antenna inside, and you would like to finish the grid somehow, to terminate it with some non-reflecting walls or boundaries or layers. So to do that, we would need to create some surface that is both absorbing and at the same time non-reflecting. Now what the problem in it is? Well, first let us consider a perpendicularly incident wave. So we would have a reflection coefficient R, which in fact is given by the impedance of the absorbing material minus the impedance of the inside material divided by the sum of those two impedances. So this is the reflection coefficient equation for perpendicularly incident wave. Now, the important point is how to get the impedance. And for a plane wave, again, the impedance is given, for a harmonic plane wave, is given by a simple equation, which is well, just remember the story about electromagnetic wave. J is the complex unit, omega is the angular frequency, 2 pi f, mu is the permeability, epsilon is the permittivity, and sigma is the specific conductivity of the material. For non-conductive materials, you would cancel j omega, and the square root of mu over epsilon for a free space is 120 pi ohms, approximately 377 ohms. But then if you want to get no reflection over here, you would need to get a material that has a real impedance. On the other hand, we would like to get the material that attenuates as much as possible. Otherwise, we would not get the reflection from the boundary, but anyway, somewhere there after that material, we have to terminate the thing. So, for example, think about that as a simple termination, which is a metallic, an electric wall. So the reflection after that is big. Just we have to attenuate the wave so that it goes through the layer, attenuates very much, and if it gets reflected, it does not make it out of the layer with a significant energy. That's the trick we do in practice. Now the same we do in this numeric simulation. But the problem is that any material that should be lossy must be conductive. Conductivity is guilty for losses in dielectrics. So the problem is that once you get a lossy material, then the impedance of that material, ZA, is a complex number. And this ratio would never be zero because you have subtraction in numerator and addition in denominator. That makes, with one of the numbers being complex, a problem. Now, the impedance of the inside material, mostly air or free space, is given and is real. So this is one of the problems. And in reality, as well as in calculations, this is solved by an additional factor. In fact, this model of material is carried out to model most of dielectrics or conductors. And it fits quite well for two purposes. First, those three values, permeability, permittivity, and conductivity, are derived out of the behavior of a material, out of its reflection and transmission through that material. And they mimic it very well for most of the materials, except for one kind of materials that are more or less artificially created. We do not meet them in nature. And those are materials that do exhibit both electric losses and magnetic losses. Well, in fact, we talk about specific conductivity, but the fact is that we just calculate this conductivity to fit the losses of the material. If you take, for example, a piece of glass, it a little bit damps the wave propagating through it. So it's lossy. It's not true that there is any conductive current flowing through the glass. It's an insulation layer. But the fact is that the small domains within the glass get polarized by the harmonic wave in opposite directions. And when repolarizing, some part of the energy of the field is converted to heat. But in our model, this is represented by conductivity. So it's more or less a parameter that would create the property, although it's not a real conductivity. Now, some materials could also exhibit magnetic losses. That is, again, there are small domains, small magnetic domains, and you can repolarize them by a harmonic wave. And this repolarization consumes some energy. And so for this purpose, the classic theory is enlarged by one term, which is the losses by repolarization of magnetic domains. historically it's also denoted by sigma, like electric conductivity, just this must have a different dimension, so it's just a historic way to name it. And if you have a material that has both electric and magnetic losses, then you can again balance it so that you get a real value of impedance, but losses within the material. Now you would get a material that does not reflect the wave at the boundary and attenuates it inside. While this is quite difficult to be created, and that's a difficult task for chemists, for chemical engineers, this is quite easy to do in equations. You just prescribe some value of losses, both electric conductivity and both magnetic dissipation. Now, although this is very fine, it has one problem, and that's the problem of non-perpendicular incidence. If the wave comes with other direction, then there is some reflection even from this surface. We would have to put down equations for arbitrary angle incidence of a wave and a boundary. But anyway, if you do not have a perpendicular incoming wave, then you would have some reflection. In order to decrease that, there is a trick used, which is the same in numerical simulation like in practice. And what you do is you use a sandwich structure. A sandwich structure which has several layers. So that the first layer has some small losses, but it has mostly the same impedance and mostly the same propagation constant, like the free space. So there is some very small reflection, but most of the wave gets inside. But yes, it is not very much damped, because that material is not very much lossy. But after all, there is a second layer, which is a little bit more lossy. And yes, there is a reflection at the boundary from the first to the second material. But this wave reflected back gets a little bit damped on this way and a little bit damped on this way. So finally, you would get sufficient attenuation, and this story repeats so that, say, 5 to 10 layers of material which with increasing damping factor and increasing reflection at non-intended angles is contained in the matching structure. But after all, at the end, you would have some good damping of signals or waves that could be, let's say, minus 60 dB under the level of the main signal. The second trick is contained in here, that if you have a wave that goes directly to the boundary and back to the area of interest, to the antenna, then this wave comes under an angle which is close to perpendicular, and the matching structure is designed for that, and there is low reflection. Now, if you have a wave that makes it under quite different angle, then you have several reflections which are not zero but small, so then you get sufficient damping before the energy returns to the area of interest. So this is the first concept, which is mostly named like perfectly matched layer. You have a layer of lossy dielectric, you modify both electric and magnetic conductivities so that the reflection is very low and there are some losses, and you possibly use several matched layers stacked one on top of the other. So this would be something that would enable you to carry out simulations pretending that there is an infinite mesh, but instead of that infinite mesh that would cause infinite computation time, you make the mesh smaller by incorporating perfectly matched layers. So this is an important idea that is used in finite difference time domain calculations in the case that you should simulate an open problem. By open, I mean a problem that is not closed within magnetic or electric walls. Questions? If there are no questions, I will only shortly comment on other possibilities. There are, of course, even more sophisticated methods like stacking a number of layers. While this is done in technology, I mean, there are sandwich materials that can be bought and, for example, glued to a surface of a metallic object to diminish its reflections. So this is something that could be elaborated in practice. Numerical simulation can easily handle things that are impossible in practice, but as a numerical model can provide a non-reflective termination of a grid. And this is mostly achieved by a set of equations that mimic anisotropic or even anisotropic materials in which both permittivity, conductivity, and other properties of the material are orientation dependent, which tries to keep the energy inside the material so that you get the energy then does not propagate through but propagates along the layer and does not get out. So this is the trick of, for example, uniaxial perfectly matched layer, something that does not exist in the nature. You can't construct it and sell it, but you can make a numeric model of such an environment. And this is good for damping reflections. That is something that could provide with minus 100 dB of reflection or return losses. So that's one important point. The boundary conditions mimicking free space. Now let us touch a few more points on FDTD. Let's revise back the conditions to set up step size and through that the numerical burden of calculations you have to do to solve your problem. So first, let us put down the current Friedrich-Levy condition for time step. We already touched that earlier. So we have to keep the time step smaller or at maximum equivalent to 1 over c, where c is the velocity of propagation of light or electromagnetic wave, divided by 1 over square delta x plus 1 over square delta y plus 1 over square delta z or if the discretization steps in x, y, and z are equivalent, you could just multiply the delta x by a square root of 3 and get the result. So this is the condition for stability of a finite difference time domain leapfrog algorithm. Now you have to cut at least at least 10 cuts per wavelength for rough calculations and let's say 25 cuts per wavelength for precise calculations. Now this is a set of conditions, and now let us think it in a real case. For example, you have a resonator. A brick-shaped resonator that is to be investigated. By the way, this is something that has an analytic solution, so we just use it as an example. So you have such a resonator that is partly filled by a dielectric. Let's say that half of that resonator has the relative permittivity of 4, while the rest is free space. And now we will have to investigate this resonator by a finite difference time domain, for example, in order to find resonant frequencies. Again, we would not do that in this shape because this has an analytic solution, but for example, if there is some irregularity in the filling, it's not just a plane, but there is some more complicated geometry, then we would have to resort to finite difference time domain. Let's have 10 100